Next, we will learn the ratio test, which is one of the two tests for absolute convergence. That means they do more than just test for convergence. They test for a stronger type of convergence, the absolute one. But we know from one of the previous lessons that if a series converges absolutely, then it converges. And let's discuss the ratio test. The ratio test is asking us to set up the limit of the ratio of a successor over its predecessor in absolute value terms. So you find this ratio and find the limit of this ratio, more importantly, and then you have three possible choices. So that limit could be less than 1. In such a case, your series converges absolutely. Your limit could be greater than 1. In such a case, your series diverges. And the limit could be equal to 1. And in such a case, the test is inconclusive. That's it. And we know if a series, if series converges absolutely, then it converges. So we can determine the convergence of a series by running this test as one of the convergence tests. So let's give it a try. We have a series, and the question is to determine whether it converges or diverges. And we're going to stick to the plan. So first we're going to try to recognize this as a geometric. It is not. Is it telescoping? It is not. Is it P series? It is not. Next, we're going to set up the divergence test. And in this case, the divergence test is inconclusive. And therefore, we're going to move on to one of the convergence tests. And we're going to try the ratio test. And to do the ratio test, we're going to set up that limit as n goes to infinity. The absolute value of the nth term goes in the denominator, and the absolute value of the n plus 1th term goes in the numerator. Now, since everything is positive in this expression, we don't need the absolute values, and we simplify this by writing it as a single fraction. Now 5 to the power n and 5 to the power n plus 1 have a lot in common, so we can reduce the whole 5 to the power n, and we end up with something like this. Now this is a simple rational function whose limit is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. So the answer is 1/5, which is less than 1, and therefore the conclusion is that this series converges absolutely, and the reason is the ratio test. Alright, so let's try another example. This time I'll just set up the ratio test to save time. to set up the ratio test as a limit as n goes to infinity. The nth term is in the denominator, n plus 1th term is in the numerator. Since everything is positive, we don't need the absolute values, and we can rewrite this whole thing as a single fraction. n plus 1 factorial times 7 to the power n divided by n factorial times 7 to the power n plus 1. n plus 1 factorial and n factorial have a lot in common, so we can reduce the entire n factorial. And 7 to the power n and 7 to the power n plus 1 also have a lot in common, and we can reduce by 7 to the power n. So as a result, we have the following limit, and this limit goes to infinity, which is greater than 1. Therefore, the conclusion is that this series diverges by the ratio test. And when series diverges, it is very possible that you will be able to determine it by applying the divergence test. However, in this case, I decided to skip it. All right, let's do one more example. And I'm not saying that the ratio test is the best test for this problem, but let's still go ahead and apply the ratio test just to see how it may work out sometimes. So we're going to have the absolute value of the nth term in the numerator, and we're going to have the absolute value of the n plus 1th term in the numerator. I think I misspoke earlier. One is the numerator, the other one is denominator. Same reason as before, everything is positive, so we don't need to have it written with absolute values. And now we simplify this complex rational expression by simplifying everything. And this is what we have. We can simplify it further. And you can see that what's in parentheses is 1, and 1 raised to any power other than infinity, or negative infinity, is 1. So the test is inconclusive. What does that mean? That means we will have to use another test to determine the convergence or divergence of the given series. In this case, it's clearly P series, and P is greater than 1, so this clearly converges. But the reason is not the ratio test, it's P series with P equals 8 over 7, and which is greater than or equal to 1. So you have learned the ratio test and have seen how it's applied to determine the convergence of a given series.